Good afternoon, ladies and gentlemen. Today I'm going to present our work titled Attention is All You Need, an Interpretable Artificial Neural Network Architecture. This is a jointly work with the Department of Complexity Science in Potsdam, Germany. Let's move on. A brief outline. I will start by introducing the problem, then I will present our attention approach, followed by some results and concluding remarks. Now, the world is dynamic, and building models to describe its unfolding is a very important task in almost every area of science and engineering. Here in this work, we are focused on the study of the global dynamics of a given system by means the study of the long-term behavior of a given system for different initial conditions and or parameters. So this kind of analysis is indeed extremely complicated, let's say, even for very simple systems. So imagine how hard can be this type of investigation for complex system where we have multiple objects that are interacting together in order to construct highly dimensional behaviors. And unfortunately and or fortunately for us, these systems are present in a wide range of environment like micro and nanosensors, weather, power grids, and so on and so forth. And accomplish a global understanding of their effect is thus a very important task, but it's extremely challenging. And it's not just challenging because actually at the state of the art, the study of the global dynamics of complex system is still computationally extremely challenging, and the curse of dimensionality associated to this kind of problem is still an unsolved problem. Now, here comes our main objective, which is the goal of our approach. Let me start by arguing about the uniqueness of the representation of a given dynamical model. The best model actually does not exist. There is an infinite number of models describing the unfolding of the same system. And here in our work, we look for an highly interpretable representation of a certain dynamical system in order to simplify the study of the global dynamics of a given model, of a given system. And to do that, we will leverage on tools like artificial neural networks. So actually, with our approach, we try to make paradigm shift. So instead of developing a tool to study the global dynamics of a given model, we try to develop a tool to reframe the representation of a given model in order to simplify the study of the global dynamics of the subject, the observed system. And the main idea is that dynamics simplify around certain special solution and region of the state space, like attractor, invariant manifolds. And our approach actually try to construct suited models, extremely simple, extremely interpretable, around those specific regions of the state space. So for each of these specific special region where we may have different behavior of our system, we have suited we try to construct suited dynamical model representative of that specific region. So we end up with an ensemble of lots of models, highly interpretable models that can be representative of, for instance, normal form of universal oscillators like the Duffing oscillator, or maybe something even simpler like a model that it's which goal is just to represent the dynamics of a limit cycle, or another one of a fixed point, and so on and so forth. But this is not enough to make the overall model interpretable. We need something more. We need a tool that actually tells how, where, and when actually one of these highly interpretable model is responsible for the description of our dynamics, and how all of these submodels are interacting together in order to construct the overall dynamics. We need something that put the attention on the right place. We need an attention mechanism that actually, looking at the state of our system, it's able to give us as output a vector of weights, where each weight is representative of how much a given model is responsible for the description of the dynamic in that specific location of the state space. And this can help us to actually have this really nice interpretation about how the state space is subdivided. And we can actually see the this really well structured interaction between these highly interpretable models that make the overall framework extremely interpretable. So here comes our final ensemble architecture, where we have this set of simple models all stacked together, represented by trainable artificial neural networks that are actually interacting together to reconstruct the overall dynamics through the attention mechanism. And as now we are trying to frame an optimization problem, we have to develop a tool that guides this optimization process. We need a loss function. Our loss function is made by three terms. One terms that actually promote the fitting procedure of the vector fields of the observed dynamics. The second term actually promote or ask to the attention mechanism to converge to a small set of simple models that are working in a specific after a certain transient. So after a certain transient, we are asking to our overall model and to our attention mechanism to converge to a really small and sparse set of models that are representative of our dynamics. And then we have an additional term that asks to the attention mechanism to behave as a quasi-monotone function, thus as almost a Lyapunov function. So then we apply our approach to two canonical examples, like the Lorentz system, where we had extremely nice results in predicting and constructing the chaotic attractor related to the system. But this is not the point of our talk here. The main outcome given by our ensemble network is the attention mechanism, is the outcome given by the attention mechanism. And you can see here at the bottom left this really well structured interpretation and partition of the state space, where we have actually the dynamics of our system that in this specific case is described by two linear systems, one that is the red one and the other one that is the blue one, that are symmetrically disposed in subdividing located in subdividing the chaotic attractor. And yes, so we have this really we can clearly see that we have this really nice interpretation of how the global dynamics in this case is, or of our system is organized in the state space. And we are also able, thanks to this approach, to identify the location of the two foci point representative of the Lorentz attractor. And here are also other results where we tested the long-term prediction of the recovered model. Indeed, we have extremely good results. We achieved extremely good results, and also the speed in the training is extremely high. So we don't need lots of epochs, let's say. But this is because we are training extremely simple networks that are, as we said, are responsible of the description of really simple behaviors of our system. Then we apply our approach also to a single Kuramoto oscillator that is described by that shows two main attractors, a fixed point and a limit cycle. Here is at the left, the true basin of attraction reconstructed from the original model. At the right, we have the one reconstructed with the recovered model. And you can see that actually the match is perfect. Again, of course, the recovered model it's working extremely well, but this is not the point of our talk. As I said, the reconstruction of the basin of attraction with our new model is indeed still computational demanding as much as the previous one. Except for some special cases where we are just trying to reconstruct the dynamic using linear models, then we can use the integrability property of a linear model to speed up a lot the process of the reconstruction of the basin of attraction. But this is not the point of our talk, because what is extremely efficient and what is the really where we should put the attention is on the attention mechanism that give us this really nice outcome, that give us this really nice interpretation of how the global dynamics is organized in the state space. Here we have we can clearly see that there is a linear model working in the neighborhoods of the fixed point. That is the linearization of the real model. And we have an additional model that is working around instead of the limit cycle. Here we have two case study. In one cases, we promote more disparity among the models. That's why we get a more sharp attention mechanism. And then we apply finally our approach to a network of Kuramoto oscillators. We generate data by taking one nodes and perturbing it in the large displacement field, obtaining a set of time series. Actually, this type of models are able to describe many different behaviors, but in our cases, with just five oscillator, we observe just two main behavior: the complete synchronization and the solitary state. And again, finally, we obtain a really nice interpretation about how the phase space is how the global dynamics is organized in the phase space. And looking at the attention mechanism, we actually made a slice in the state space by just looking at the state of the perturbed node, and we can clearly see that we have below a certain frequency a model that is dominant, that is the one related to the solitary state, and that is intrinsically indeed four-dimensional. So we got really this nice interpretation about the system dynamics is organized. So I present our new framework based on artificial neural network to recover highly interpretable model of complex system for the study of the global dynamics that was tested to two canonical systems, and to also present some preliminary results about a network of Kuramoto oscillators. Thanks for your attention.